In this video, we'll go through the Chapter 4 review. This review is broken up into sections, so we'll begin with section 4.1, which was on exponential functions. The directions here are simple. Graph each of the following. So let's zoom in and do each one. On number 1, we have a function with an exponential function with base 3. So again, for the original, the y-intercept is at 0, 1, and then the base, which is 3, you can see will give us that point right there. So this is the point 1, 3. That again is for the original. This plus 1 right here, though, is causing a transformation. It is with the x, so it is going to be a horizontal shift, namely in the opposite direction of what you'd expect. So it's going to simply shift the graph left 1 unit. So if we move those two ordered pairs that we did for the original left 1 unit, we could go ahead and graph the exponential function. Of course, do remember that the exponential function has a horizontal asymptote, namely y equal to 0, without any sort of vertical transformation. It's right there. So now let's go ahead and just use the green points to answer this question. And we have the graph shown right there. All right. Number 2, we have a 2 to the x this time. So the original function is going to be right there at 0, 1 and at 1, 2. This plus 4 is off to the side. It is not in the exponent with the x. Therefore, it is going to be a vertical shift going exactly the direction we expect it. So up 4. So the 0, 1 will go up to 0, 5, and then the second point will also shift up. It's also useful to move that horizontal asymptote so you know not to go too far down. So here we have the horizontal asymptote, y equal to 4, and we'll go ahead and use these points to sketch the shape of the exponential function given. All right, in the case of 3, we have another vertical shift with the minus 2. But remember, order of operations, the multiplication by that negative 1, which is a reflection. So that negative in front of the 3 to the x is a reflection over, and again, let me go through the reasoning. It is not with the x, so it is with the y. So the positive y's will be made negative, so it's going to be a reflection over the x-axis. Then the minus 2 will simply shift the graph down 2. So the original is, let's go ahead and do that in blue for consistency. So 0, 1, and the base is 3, so 1, 3. So 2 transformations. First, I'll reflect those over the x-axis, so that'll give me those red points. Then I'll shift those red points down 2 units. And it also shifted the horizontal asymptote down 2 units. So with that, the answer is right here in green, the exponential function right there. And one more. In the case of 4, we just have a reflection. This reflection is going to be over the y-axis because the positive x's are made negative and vice versa. So that is going to be, as I stated, a reflection over the y-axis. The 2 to the, so the base is 2, so those will be our, let's go and put that in the right spot. Right there are the original points. The point in the first quadrant will end up in the second, and again, the one on the y-axis does not change. The horizontal asymptote is still y equal to 0, and we'll go ahead and sketch the shape of the graph. All right, so that covers the first 4 exercises. The other couple comments that I should make here, these of course are given the we're given the function and then we need to graph it. You should also be comfortable going that the other way. So that is to say, if you were given this, go ahead and get back to this. So again, just kind of reversing the reasoning, you would just check essentially where the y-intercept is, and if it was a decreasing function, that's because you have the negative in front, or realize that this is also 1 over 2 to the x. We've also talked about the domain and range. If it's not on the review, don't stress too much about it, but the domain in general is going to just be negative infinity to infinity, and the range will depend on transformations and the like. So review back the notes if you would like a refresher on that. All right. In section 4.2, we learned about the logarithmic function. And in the first two exercises, we're going to write the equation in its equivalent exponential form. As we go through this, I would always encourage you to pause the video and just see if you could do them ahead of me. But let's go through these and make sure we're able to write it in the exponential form. So we're given in the logarithmic form, and it's a little bit weird this time. I think in the initial exercises we were given it something like log base 3 of 13 is equal to b, but again, you could rewrite this if you would like. So to write an exponential form, identify the base. The base here is 3. The base of the log becomes the base of the exponent, which is from the other side. And then whatever is the input to the logarithmic function is what the exponential form is equal to. No need to solve for b, and again, technically we already solved for b right here. That's just some irrational number that you could go ahead and get by plugging in into a calculator. Actually, it doesn't have to be irrational. So in the case of number 6, the base of the log is x, so that becomes the base of the exponent, which we get from the other side. And then you set that equal to whatever the input of the log was, so it's equal to 20. No need to simplify those, we've switched it to its exponential form. Now to go to the logarithmic form, we're going to just reverse that process. So the base of the exponent, which is 4, becomes the base of the log. And again, just zooming in, this 4 is a subscript, so make sure you write that carefully. So the base of the log comes from the base of the exponent. The input to the logarithmic function is what was the number farthest away from the base. And then, of course, you set that equal to whatever the exponent was. All right. In the case of number 8, we get log. The base of the exponent is 7, so that's not the base of the log. So log base 7 of 9 is equal to x. All right. These next 4 were asked to evaluate without a calculator. So remember that the logarithm and the exponent are inverses. So the log, the base, I can't change the log base 7. But 49, I can go ahead and rewrite 49 as 7 squared. The thought process is I want to get matching bases, and because they're inverses of each other, they'll simply cancel, and it'll be equal to whatever the exponent was. Couple more exercises like so. Notice here the base is larger than the input, so we can't change the 16. So you may want to think, okay, it's sometimes easier to say, oh, I know that 4 squared is equal to 16, and I want 16 here, so how can I turn 16 back to 4? By taking the square root, which of course is just by the 1/2 power. So the cancellation of the matching bases means that the answer is 1/2. In the case of number 11, we have a log base 2. And then if you just ignore the fraction part and just think about like this in terms of 16, well, I know that 16 is simply 2 to the 4th. Now, I do need to consider the fraction, so it's -4. And then we'll go ahead and cancel. So -4 is the answer to 11. And lastly, 12 is pretty straightforward. Just remember that when it's not specified, this is the second or the square root. So this is 3 to the 1/2 power. So again, the answer here is 1/2. All right, to do maybe a couple extra exercises just to make sure we see the whole gambit. Of course, go back and look at the 4.2 lesson. Some additional ones that I should go ahead and mention is like, what if we had log base 2 of 1? Well, this would just be the same as log base 2 of 2 to the 0. So the answer is 0. We've also looked at a scenario where you have log base 2 of 2. And then you just remember that it's understood that the exponent is 1. So the answer is 1 there. And just to do a little bit of variety, let's say we have log base 2. And then let's say we have the 5th root of 2 to the 4th. So this could be rewritten as log base 2 of 2, and the exponent on the 2 is in the numerator of the fraction, and the index of the root is the denominator. So the answer to this one is 4/5. So just to get a good variety of questions, there's a few additional examples. Let's actually do maybe 1 or 2 more examples. Now I think about it, there's nothing here about the natural log. So let's suppose we also have like ln of e squared. Well, remember that when you see ln, the base is assumed to be e. So this means we could directly cancel the e's, and the answer is 2. In a similar way, if we have something like log of, let's say, 100, well, the base is not specified, so you assume it is 10 by convention. So this is the same thing as log base 10 of 10 squared, so the answer is 2. We may see some of those later, but just wanted to do a couple extra examples. All right, now into section 4.3. We're asked to first use the properties of logarithms to expand each of the logarithmic expressions as much as possible. And then after you expanded it, it might be possible to do some simplification. Again, I would encourage you to maybe pause and just see what you remember, but let's go through them. In the case of 13, we have log base 3 of 27 times y. Multiplication in the input of a logarithm means that you could write the product separately, where each product gets its own log. And then what you would do to the logs is, because it's multiplication, you would add those logs. All right, we can simplify this. 27 is 3 to the 3rd, so that cancels, and then we're just left with a 3 here. And nothing more to do with log base 3 of y, so this is our final answer. All right, sliding over to 14. We are going to apply the quotient rule because there is, of course, a quotient. So this one feels the same as the first. We have log base 4 of x. The numerator gets its own log. The denominator, log base 4 of 16, because the 16 gets its own log. And then because it's a quotient, the quotient rule says we simply subtract the logarithms. So this is log base 4 of x. And then again, 4 is simply 16 is 4 squared. So the 4's will cancel at the log. So this is just minus 2. This is written correctly. Just remember that this right here is implying that the parentheses are around the x. So this would be different, but so let's not put that because that would not be correct. In the case of 15, we would use the product rule, and the product rule says whatever power is on the input of the log could be moved in front as multiplication. So this is 2 times log base 3 of y. In the case of 16, you may want to just rewrite this first as a fractional exponent. So this is going to be x to the 1/3. Again, just as stated earlier, that's assumed to be 1 there, so that's why a 1 is in the numerator and the index 3 is in the denominator. Again, the power rule says the 1/3 could come out in front and is multiplied by log base 5 of x. Again, the bases are not changing. Those are fixed at whatever was given in the problem. All right. In the case of 17, we have log base 3, and that whole quantity, x plus 1, is raised to the 1/2 because it's all in the square root. Now, power rule says that 1/2 comes in front, and then we have log base 3 of x plus 1. And as mentioned earlier, the parentheses here are important because that maintains the grouping. If they weren't there, it would just be on the x. And one other thing to remember, don't distribute. A logarithm is a function, not a number, so again, do not distribute. This right here is our answer. And now 18, we have the log base 2 of 8 times x to the 5th. So the product rule says the log base 2 of 8 is added with the log base 2 of x to the 5th. And we can do some simplification. 8 is technically 2 to the 3rd. So the 3's, this will simplify to just 3. And then we'll add to that, well, the 5 comes down in front, and we still have multiplied by log base 2 of x. All right, so that is the expansion of logarithms using their properties. We could also go to the other way, that is to say we could condense it, use the property of logarithms to condense these. And we're told to write the expression whose logarithmic coefficient, single logarithm whose coefficient is 1. That is to say, make sure you undo the power rule putting on the exponent. And technically, we should go ahead and just cross out the second direction. As you can condense them, you won't want to go ahead and do any sort of simplification. All right, so number 19. There's two things that we're going to need to deal with. The numbers in front will need to go up on top first to undo the power rule. So we'll have log base b of x squared plus log base b of y cubed. So that's what that second sentence said. That is to say, write the expression as a single logarithm whose coefficient is 1. So that handles the coefficient is 1 part. Now, we have a product rule because of the addition. So we write the single logarithm, same base as before, and you just multiply the x squared and then the y cubed. And again, since it's multiplication, I'll just write them next to each other. In the case of number 20, same principle except for the quotient rule. So we have log base 2 of x to the 1/2 minus log base 2 of y to the 5th. Just dealing with those coefficients, the numbers in front first. And then we write this as a single logarithm, log base 2. And then in the numerator is the positive log, so that's the square root of x, and that'll be divided by whatever was in the input of the negative log, so that is y to the 5th. So again, if you want to, just to kind of make sure that, since we don't have lines and things, I'll just do that to go ahead and combine them. That's not necessary. But one thing that I do want to caution you of, I see the common mistake is applying the quotient rule, but still keeping more than one logarithm. So this is kind of like halfway there, but this is wrong because it condenses down to one logarithm. So be careful with that. And then 21 is just a little bit more challenging than the previous two because we have 3 logs, but they're all base 7. So the first step is just to go ahead and use the power rule to put all of the numbers, the coefficients on top. So that's log base 7 of x cubed plus log base 7 of y to the 5th minus log base 7 of z to the 1/2. So when we condense all of these, there's two things I'll do. I'll also write that as a square root as I go, but anything that has a positive, so let me emphasize this with some color. So that's positive, that's positive. So the x and the y will be in the numerator. So we have log base 7. One of those, because we condense down to 1, so we have an x cubed and a y to the 5th. And then it'll be divided by whatever was inside the negative log. So it'll be just the square root of z. So that completes section 4.3's review. One last section, 4.4, where we solved exponential and logarithmic equations. So in 22, we're solving an exponential equation. The thing that you'll try to do first is get matching bases. So if I look at my bases are 2 and I see a 64 right here, technically to the 1 power, but I notice that 64 is a power of 2. So what I'll go ahead and do is rewrite 64 as 2 to the 6. Then the 2 and then the 4x minus 2 will come down, as will the equal to sign. We have matching bases, so we don't really need them because the exponents could simply be equated. And we have 4x minus 2 is equal to 6. Essentially what I did is I took log base 2 of both sides. A little sloppy there, but then all of those, the bases will cancel, and then the exponents are what is left. All right. So now that we have that done, we have a linear equation. So I'll add 2 to both sides and divide by 4. So I get x is equal to 2. You can always plug that in to check it. We don't need to for exponential, but 2 times 4 is 8. Minus 2 is 6, so 2 to the 6 is equal to 64. All right, in the case of number 9, with number 23, we have 9 times e to the 5x is equal to 90. So order of operations, when you're solving, you do it backwards. So I need to deal with the division before I deal with the exponent. So just doing my order of operations backwards. So we get e to the 5x is equal to 10. Then, because it's the natural number e, I'm going to take the ln of both sides, because there's no way to get matching bases here. There's no way to turn 10 into an e, so I'll take the natural log of both sides. Again, the base here is e, so it cancels, and we're left with 5x is equal to ln of 10. And then we divide both sides by 5. So x is equal to ln of 10 divided by 5. It is important to remember not to simplify anymore, because that 10 is being protected by the ln, so you can't divide that. And ln of 10 is a number. You can always verify that by just doing, like in some sort of calculator, doing ln of 10 and divide that by 5. So that's about 0.46. And again, if you were to divide, ln of 2 is something very different. So be careful with that. All right, going back to the lesson to finish it off, we have to solve 2 logarithmic equations. In the case of 24, this is probably the simpler version because you just have to switch it first to its exponential form. So 4 to the 3rd is equal to 3x minus 5. Again, the base of the log becomes the base of the exponent, which I get from the other side. Whatever was inside is what we set equal to. So 4 cubed is 64. And then this is equal to 3x minus 5. Adding 5, we get 69 is equal to 3x. And dividing by 3, we get 23 is equal to x. So technically, whenever you are solving a logarithmic, you should go ahead and check your answer. Here we won't have any issues, assuming we did our computation correctly because there was nothing square that got rid of negatives. But if I check, I get log base 4 of 3 times 23 minus 5. I'm checking if that's equal to 3. Simplifying the left side, log base 4 of 69 minus 5 is 64. It's equal to 3. And yes, it is, because again, 64 is 4 cubed, bases cancel, answer is 3. So our solution set here is just the single value of, careful to not put 3, but the one you found up above, which is the 23. In the case of 25, you will need to essentially condense this down first into a single logarithm, then do the same principle. So when you condense this using the product rule, you have log base 2, and then you're going to multiply the x plus 3 and the x minus 3, and it's going to be equal to 4. Technically, you could switch here, but I'm going to go ahead and simplify inside first. So we have, again, bringing down the log base 2. If you FOIL this out, you get x squared. And outside and inside are plus and minus 3x, so those will cancel. And you have minus 9 equal to 4. Now we switch. 2 to the 4th is equal to x squared minus 9. 2 to the 4th is 16, so that is equal to x squared minus 9. Add 9, you get 25 is equal to x squared. And then now here you take the square root of both sides, and you do get x is equal to not just plus 5, but plus or minus 5. So you should go ahead and check both of those in the original. And remember that the domain for a logarithm is essentially only positives. So we have to make sure that we have a positive value inside of the logarithm. So just to kind of to shortcut this a little bit, x is equal to 5. When you check this one, what will happen? Well, you'll get log base 2 of 8 when you plug that in, plus log base 2 of 5 minus 3 is 2. And if that's equal to 4, then again, you can verify this. Yeah, this is 3 plus 1, and that is equal to 4. So 5 is part of our solution set. And then if you were to go ahead and check x equal to negative 5, you could probably mentally see that we're have an issue, because we'll have log base minus 5 plus 3, just plugging it in here, minus 5 plus 3 is going to give you a minus 2. And technically we could stop there because this is the issue, that logs are not defined for negative inputs. So you can, I mean, yes, there's a little bit more that you can do, but at this point you can just say, okay, we discard x equal to negative 5. So our solution set is just going to be the single number, namely 5. So I hope you found this review beneficial, and congratulations, that really completes this course. So study hard as you prepare for the final and your last test, and good luck.